While many of us speak different languages, the number system we use is almost universal. All around the world you see the digits 0 through 9, which is also referred to as the base 10 number system. So, if we all use 0 through 9, why do computers use zeros and ones, or a binary number system? Wouldn't it be a lot easier if computers used the standard base 10 system? Well, yes, it would be a lot easier if computers were able to use the base 10 number system. But this video will discuss the underlying structures that make up a computer, and why those underlying structures lend themselves well to a binary number system. Often, you will hear the following line of reasoning to why computers use binary numbers. First, the fundamental building block of a computer is a transistor, and the transistor can be thought of as a switch in a digital system. Since a switch can only be in an on and off state, this must be where the zeros and ones come from. The first two parts of that argument hold up for a computer. The underlying building block of a computer is a transistor, and we can still think of a transistor as a switch in a digital system like a computer. However, when we actually examine the internal structures of a computer, the switch-like nature of a transistor and the on and off nature of a switch are not the real reason we use zeros and ones when discussing computers. Maybe more surprising, computers are not really using zeros and ones at all. To break down the real reason for using a binary system when discussing computers, let's first look at how transistors are used in computers. A way to think of how a transistor is used in a computer is like how a faucet is used on a sink. When the faucet is off, the water is held back. However, when the faucet is opened, the water can flow. Of course, transistors are not passing water. Instead, a voltage is attached to a transistor. You might be familiar with hearing the term voltage when using common household items, like that pesky 9-volt battery that chirps in the smoke detector. Going back to our water pipe example, a simple mental model for voltage maps well to the water pressure in a pipe. Having a higher water pressure would be similar to having a higher voltage. If you are not a water pressure expert, another way to relate the concept of voltage to another domain is to think of the relationship between potential energy and gravity. As you hold a ball higher in the air, it has the potential to go faster when dropped. But until dropped, that potential to go faster has not been realized. With voltage, we are concerned with the potential in relation to the charge of the system. Both negative and positive charges exist in the system, and the negative and positive charges are attracted to one another. A balanced, or neutral state, where the amount of negative and positive charge is equal, is then preferred by the system. A voltage is then a difference in the charge between two locations. So a higher voltage represents a greater difference in charge between two locations. This difference represents a potential that can be utilized once the transistor, acting like a switch, turns on, similar to when the faucet was turned on or the ball was dropped. While a variety of different voltage values can exist across a transistor, a digital system is designed to ensure that two voltages are used in the system. For example, a computer could be designed with two voltages of 5 volts and 0 volts, or 1.8 volts and 0 volts, 1.2 volts and 0 volts, or many other pairs of two voltages. The goal to design computers with these two voltage levels is why zeros and ones are discussed so often for a computer. We abstract away the need to know the specific voltage levels. This abstraction is very useful because now we have a common way to discuss and compare many different computer implementations. There is one slight problem though. In certain scenarios, a transistor does not pass the full input voltage to the output. This would be a problem for computers because there are often many stages of transistors connected to one another. Going back to the water visualization, if we lost some of the water every time it went through a switch, then eventually there would be no more water left. To solve this issue, we actually have two different types of transistors in computers. Since we now know that we can abstract two voltages of the system with ones and zeros, I'm going to use ones and zeros to discuss functionality, but feel free to use a specific system like logic 1 equals 1.8 volts and logic 0 equals 0 volts to connect the discussion of zeros and ones to specific voltage values. Okay, so our first type of transistor turns on when a logic 1 is applied to the transistor, and it is good at passing a logic 0 when turned on, meaning that in our water analogy, essentially no water is lost. However, if a logic 1 was applied, we would get a voltage not equal to the original value at the other side of the switch. The second type of transistor turns on when a logic 0 is applied to the transistor, and is good at passing a logic 1, which again can be visualized by losing little to no water. However, if a logic 0 is applied, then we end up with a voltage that does not equal the logic 1 or logic 0 case. To ensure that we always end up with a logic 0 or logic 1 at the output of our circuit, we use both types of transistors, or switches, in what is referred to as a complementary fashion. For example, consider this circuit. There are two inputs, named A and B, coming from a previous stage in the circuit. The input values are 0 or 1, or 0 volts or 1.8 volts if we wanted to remove the 0 and 1 abstraction. The top section of the circuit contains switches from the second category, where the switch turns on when a 0 is applied and passes a good logic 1. Since these switches are good at passing a logic 1, we connect a logic 1 to one side of the transistor, where logic 1s will be designated by the color green. The bottom section of the circuit is constructed out of the types of switches that turn on when a logic 1 is applied and pass a good logic 0. The logic 0 is connected to one side of these types of switches and will be denoted by the color red. So let's look at how those zeros and ones travel to the output as the values of A and B change. When both A and B are 0, both of the switches on the top section of the circuit turn on and connect the logic 1 to the output. So the output is a 1 in that case. When A is 0 and B is 1, one of the paths on the top section connects a logic 1 to the output, and because both switches on the bottom path are not turned on, that path is not connected to the output. The case when A is 1 and B is 0 is very similar, where now the other path on the top section is connecting a logic 1 to the output. Finally, when A is 1 and B is 1, both paths on the top section are not activated. But now the bottom section has both switches turned on, connecting a logic 0 to the output. Such a configuration ensures that only the top section or the bottom section is on for any given input combination of logic 0s and 1s, ensuring that the output is a logic 0 or a logic 1. This is what we wanted. We ensured that the circuit can now pass a logic 0 or logic 1 from one stage to the next, meaning that we stuck to only using two voltage levels and could thus still use the abstractions of zeros and ones. So, to summarize the main takeaways from this video, transistors do act like a switch in computers, and in some ways are like a water faucet. However, instead of transferring water, when the switch is on, we pass voltage from one side to another. The voltage levels in a computer are designed to stay in two states, and these actual voltage levels differ from computer to computer. The use of two voltage levels throughout the computer is the real reason we use zeros and ones when discussing computers, and the abstraction from voltages to zeros and ones helps remove the need to discuss some of the underlying system-specific details. Lastly, we actually need to use two different types of transistors and connect the transistors in complementary fashions to ensure that the internal voltages of a computer stay in those two states. If you enjoyed learning about why we use zeros and ones to describe computer functionality, make sure to like and subscribe. If you have any questions or have topics you are interested in learning about more, leave a comment down below.